Welcome back to Neural Networks Explained. Today, we're diving deep into one of the most fundamental activation functions in deep learning, the sigmoid function. By the end of this video, you'll understand exactly how sigmoid works, why it was revolutionary, and why modern networks have largely moved away from it. We'll cover the mathematics, implement it from scratch, visualize its behavior, and discuss its pros and cons. So, grab your coffee and let's get started. Before we jump into sigmoid, let's quickly recap what activation functions do. Imagine a neural network without any activation functions. It would just be a series of linear transformations. No matter how many layers we stack, we'd end up with just one big linear function. That's where activation functions come in. They introduce non-linearity, allowing our networks to learn complex patterns and relationships. Think of activation functions as decision makers at each neuron, determining how much signal should pass through to the next layer. Now let's meet our star, the sigmoid function. Mathematically, it's defined as sigma of x equals 1 over 1 plus e raised to the power of negative x. Let's break this down step by step. We start with e raised to the power of negative x. Add 1 to that result, then take the reciprocal. The beauty of this function is its output range. It always produces values between 0 and 1, making it perfect for binary classification problems where we need probabilities. As x approaches positive infinity, sigmoid approaches 1. As x approaches negative infinity, sigmoid approaches 0. Let's see what this function looks like visually. Notice that characteristic S-shaped curve. That's why it's sometimes called the logistic function. At x equals 0, sigmoid outputs exactly 0.5. The function changes most rapidly between x equals -2 and +2. For very large positive or negative values, the function becomes almost flat. This S shape is crucial for neural networks because it provides a smooth, differentiable transition between 0 and 1, unlike step functions which have discontinuous jumps. Let's implement the sigmoid function from scratch. I'll show you 3 different approaches. First, the basic NumPy implementation. But wait, there's a numerical stability issue here. For very large negative values, np.exp can overflow. Let's fix that. And here's how you typically use it in a neural network context. Let's see sigmoid in action with a practical example. We'll create a simple binary classifier to distinguish between 2 classes. Notice how sigmoid outputs probabilities. Values above 0.5 typically get classified as class 1, below 0.5 as class 0. This probabilistic nature makes sigmoid perfect for binary classification tasks. One of sigmoid's greatest strengths is its elegant derivative. This is incredibly convenient for backpropagation. We can compute the derivative using just the sigmoid output itself. So why was sigmoid so popular? Let's look at its advantages. First, probabilistic output, perfect for binary classification. The output naturally represents the probability of belonging to the positive class. Second, smooth and differentiable everywhere, essential for gradient-based optimization. Third, simple derivative computation makes backpropagation efficient. Fourth, biological inspiration. It somewhat mimics how neurons fire in response to stimuli. Sigmoid was instrumental in early successes like handwritten digit recognition and spam email detection. But sigmoid isn't perfect. In fact, modern deep networks rarely use it in hidden layers. Let's see why. The biggest issue, vanishing gradients. Look at sigmoid's derivative. Its maximum value is only 0.25. In deep networks, these small gradients get multiplied together, quickly approaching 0. Second problem, saturation. For inputs below -4 or above 4, the gradient becomes nearly 0, making learning extremely slow. third issue, outputs are always positive. This can cause zigzag learning patterns and slower convergence. These problems led to the development of better alternatives. Let's see the most popular ones. ReLU solves vanishing gradients for positive inputs and is computationally cheap. Leaky ReLU addresses the dying ReLU problem. Swish combines the best of both worlds, smooth like Sigmoid but with better gradient flow. Each has its place, but for hidden layers in deep networks, ReLU variants usually perform better. Don't write off Sigmoid completely. It's still the go-to choice for specific scenarios. Output layer of binary classifiers. You want probabilities between 0 and 1. Gating mechanisms in LSTM and GRU cells. Sigmoid naturally acts as a gate, controlling information flow. Some attention mechanisms use Sigmoid to compute attention weights. Let's build a complete example, a neural network for binary classification using both ReLU and Sigmoid appropriately. Let's wrap up what we've learned about the Sigmoid activation function. V. Sigmoid maps any real number to the range 0, 1, perfect for probabilities. V. It has a beautiful derivative, sigma prime of x equals sigma of x times 1 minus sigma of x. V. While revolutionary in early neural networks, it suffers from vanishing gradients. V. Modern networks use ReLU variants for hidden layers. V. Sigmoid still shines in output layers for binary classification. Remember, choose your activation functions wisely. Sigmoid for binary outputs, ReLU variants for hidden layers in deep networks. If you enjoyed diving deep into Sigmoid, you'll love our other videos on ReLU, attention mechanisms, and advanced optimization techniques. Hit that subscribe button and ring the notification bell so you don't miss our next deep dive into the world of neural networks. Drop a comment below. What activation function would you like us to explore next? Until next time, keep learning and keep building amazing AI systems.